Okay, so today we're going deep on periodic motion and waves.
Right.
You sent over some really cool notes on both.
Yeah.
And I think our mission should be to really try to connect these ideas, almost like reveal how they're different sides of the same coin,
Yeah.
when it comes to how energy moves.
I like that.
What do you think about that?
Yeah, I think that's a great way to put it.
Okay, cool.
You've provided these notes that
Yeah.
define, periodic motion, which is like
Yeah.
all the repeating movement that we see all around us.
Right.
From like a swinging pendulum to like,
Yeah.
a vibrating guitar string.
Right, exactly.
And then you've given us your detailed notes on waves and,
Yeah,
the different types of waves and how they behave.
exactly.
So it's a great foundation to start with.
Yeah, I think so too. And the question that's been bouncing around in my head is,
hey.
how does the seemingly simple back and forth
Right.
of something like a grandfather clock's pendulum relate to something? Yeah.
As complex and seemingly invisible
Yeah.
as the sound traveling from my mouth to your ears right now,
Okay.
it seems crazy to think that those two
Yeah.
could even be related.
So let's start with the periodic motion, because that's really the bedrock for understanding a lot of
Yeah.
wave phenomena.
Okay.
As your notes highlight, periodic motion is any motion that repeats itself
Right.
in a consistent cycle.
Right.
So,
Like a rhythm.
think of it as a rhythm
Okay.
that keeps going and going, always returning to its starting point.
Okay. Yeah. Like a
Yeah,
perfectly timed metronome.
exactly.
Tick-tock,
Yeah.
tick-tock.
Yeah,
Each beat happens at the same interval.
right.
And then the pendulum always swings back to that center point.
Absolutely.
And in your notes,
Yeah.
you mentioned pendulums and springs.
Mm-hmm.
And I was wondering if we could start there.
Yeah.
Because those were the two things that you thought were
Yeah.
most representative of periodic motion. Yeah, let's start with pendulums.
Okay.
So the time it takes for a pendulum to complete one full swing,
Okay.
that's its period,
Okay.
is mainly determined by its length and the force of gravity.
Okay.
So the longer the pendulum,
Yeah.
the longer it takes to swing back and forth.
That makes sense intuitively, right?
Yes.
A
Yeah.
longer swing
Yeah.
covers more distance,
Yeah.
so it naturally takes more time.
Exactly.
So what about springs?
Okay.
If I'm bouncing up and down on a spring,
Yeah.
what determines how quickly I go up and down?
So the period of a spring's oscillation.
Okay.
So that's how long it takes to complete one cycle
Okay.
of moving up and down and back to the starting point.
Yeah.
Depends on the mass attached to the spring
Okay.
and the spring constant.
The spring constant, is that how stiff the spring is?
Exactly.
Yeah.
So a heavier mass on the spring
Yeah.
or a weaker, less stiff spring
Yeah.
will result in a longer period of oscillation.
Okay. So we've got this
Okay.
repeating motion. Yep. With a predictable period.
Uh-huh.
Now, how do we connect that to waves?
Right.
Because when I think of a wave,
Yeah.
I picture the ocean or maybe a ripple in a pond.
Uh-huh.
It doesn't immediately make me think of a pendulum or a spring.
This is where it gets really interesting.
Okay.
A wave is essentially a disturbance
Okay.
that carries energy through space or matter.
Okay.
And here's the key.
Right.
While it transports energy,
Uh-huh.
it doesn't actually carry the matter itself along with it.
Okay. I
Right.
think I remember that.
Yeah.
Isn't that like a stadium wave?
Exactly.
Like people stand up and sit down,
Right.
but they don't actually run around the stadium.
Right.
The wave travels, but the people stay put.
Exactly.
It's okay.
The energy propagates.
Okay.
But the medium,
Yeah.
the water, the air, or the fans in the stadium
Yeah.
stay largely in the same place.
Okay.
The connection to periodic motion is that many waves are caused by
Okay.
something undergoing periodic motion.
Okay.
Yeah. So the disturbance can be caused by an object that has periodic motion.
Think about it this way.
Okay.
Imagine repeatedly dipping your finger into a still pool of water.
Okay.
Your finger's motion is rhythmic, right?
Right.
It has a period.
Yeah.
Each dip creates a ripple,
Uh-huh.
and those ripples spread out as a wave.
Okay.
The repeating up and down motion of your finger generates the wave.
So the source of the wave
Yeah.
can be a periodic motion.
Yeah.
And within the wave itself,
Right.
there's also a sense of repetition, right?
Correct.
I see my notes, you called it the cycle of a wave.
Yeah. A wave has a repeating pattern,
Okay.
peaks and troughs,
Uh-huh.
compressions and rarefactions.
Yeah.
Depending on the type of wave,
Okay.
this cyclical pattern is directly linked to
Yeah.
the repetitive nature of the periodic motion that created it,
Okay.
or the way the energy is being transmitted.
Okay. I'm starting to see how these ideas fit together.
Right.
Now, you mentioned the different types of waves.
My notes say there are transverse and longitudinal waves.
Yeah.
How does periodic motion play out in each?
So in a transverse wave, the vibrations occur perpendicular to the direction
Okay.
the wave travels.
Okay.
So picture shaking a rope up and down.
Okay.
The wave moves horizontally along the rope, but your hand is moving vertically, as your notes indicate.
Yeah.
These waves can even travel through empty space,
Right.
like light from the sun.
So the up and down motion of my hand is like the back and forth of a pendulum,
Yeah.
but oriented differently relative to the direction of the wave.
Right.
Got it.
Yeah.
What about longitudinal waves?
So longitudinal waves involve vibrations that are parallel to the direction of the wave's motion.
Okay.
Sound is a perfect example,
Okay.
as your notes mentioned.
Yeah.
It travels through air as compressions and rarefactions.
Compressions and rarefactions.
Yeah.
I remember you saying that these are areas where the air molecules are bunched together and then spread out. It sounds like a periodic change in pressure.
Precisely.
Okay.
So a vibrating speaker cone moves back and forth.
Yeah.
That's the periodic motion.
Right.
And pushes on the air in front of it,
Okay.
creating a compression.
Okay.
As the cone moves back, it creates a rarefaction,
Okay.
an area of lower pressure.
Okay.
This compression-rarefaction pattern travels outwards as a sound wave.
Okay.
So the periodic motion of the speaker creates a periodic variation in air pressure.
Right.
And that's what travels as a wave.
So even though the wave motion looks different side to side and transverse, push-pull and longitudinal, it still comes from a repeating periodic disturbance.
Exactly.
Okay, so I know that waves can have specific characteristics.
Right.
What are some characteristics of waves, and how do they tie back to the idea of periodic motion?
Let's go through them one by one. So amplitude is the maximum displacement for the equilibrium position.
Okay.
Think of it as the intensity of the wave.
Okay.
In a pendulum, it's how sore it swings from the center. In a wave, it's the height of a crest or the depth of a trough.
Okay.
With sound, the amplitude is how much the pressure changes.
Yeah.
And that translates directly to how loud it sounds.
Right.
Measured in decibels.
Right.
Bigger amplitude.
Yeah.
Louder sound. Bigger swing.
Okay, amplitude is like the strength or the intensity of the oscillation or the wave. What about wavelength?
So wavelength, which we write as lambda, is the length of one complete cycle of the wave.
Okay.
So picture the distance from one crest to the next.
Okay.
Or from one compression to the next in a sound wave.
Okay.
While periodic motion doesn't really have a wavelength in the same way.
Right.
If that periodic motion creates a wave,
Yeah.
the wavelength tells you how spaced out those repetitions are in space.
So wavelength is how the wave's repeating pattern manifests in space.
Exactly.
And then we have period again.
Yep.
T.
Yep.
That's the time for one complete cycle. Like in periodic motion.
Yes.
If a pendulum has a period of 2 seconds,
Yeah.
any wave it creates might also have a similar period.
Exactly.
Right.
The period of the wave is directly related to the period of the source's oscillation.
Okay.
If the source oscillates with a certain frequency, that determines the frequency and therefore the period of the wave it produces.
Okay, which brings us to frequency.
Right.
F. The number of cycles per second measured in hertz?
Yes.
I remember you emphasizing that frequency tells us how often a wave passes a point. Not how fast it's traveling.
Exactly.
Okay.
Frequency tells you how rapidly the cycles are happening.
Right.
While wave speed tells you how quickly the disturbance is propagating through the medium.
So how does the wave speed relate to its frequency?
So there's a fundamental inverse relationship between frequency and period.
Okay.
F equals 1 over T.
Right.
If you know one, you automatically know the other.
Okay.
Shorter period, higher frequency, and vice versa.
Yeah.
This relationship holds for both periodic motion and waves.
Right, because if a pendulum swings back and forth very quickly, high frequency, the time for one swing, the period, is short.
Exactly.
And frequency and period are also related to wave speed, right?
Absolutely.
Right.
Wave speed is equal to the product of the frequency and the wavelength.
Okay.
This is commonly shown as V equals F lambda.
Right.
That's right.
And this leads me to think about how frequency and wave speed can be totally different things.
Think about it this way.
Okay.
Imagine you're watching a crowd do the wave at a baseball game.
Yeah.
You could have tons of people standing up and sitting down. and rapid succession.
Yeah.
High frequency.
Yeah.
But the wave itself could be moving slowly around the stadium.
Okay.
On the other hand, you could have fewer people participating.
Right.
Lower frequency.
Yeah.
But the wave zipping around really quickly.
Okay, I get it.
Right.
High frequency means lots of cycles per second. High wave speed means the disturbance is traveling quickly through the medium.
Right.
Okay. And that difference brings us to resonance, right? I see resonance in my notes.
Okay.
How does that fit in here?
So resonance is a really interesting phenomenon that beautifully connects periodic motion and waves.
Okay.
It happens when you apply an external force or vibration to a system.
Yeah.
And its natural frequency.
At its natural frequency.
Yeah. Every object that can oscillate has a natural frequency or a set of frequencies at which it vibrates most easily.
Natural frequency. So, like, if I tap a wine glass, it rings at a certain pitch.
Yes, that's its natural frequency. Now, if you push a child on a swing, which as we discussed is a pendulum, with a frequency that matches the swing's natural frequency, even small pushes can build up to create really large swings.
So it's like giving the system a little nudge at just the right time in its cycle.
Exactly.
Over and over.
Right.
So the amplitude of the oscillation gets bigger and bigger.
Precisely.
Right.
And this principle applies to waves, too.
Okay.
Think about blowing across the top of a bottle.
Okay.
The air cavity inside has a natural frequency.
Okay.
When you blow with air pulses that match that frequency, you get a resonant amplification of the sound wave, making it much louder.
So it's about matching the driving frequency to the system's natural tendency to oscillate.
Exactly.
Whether it's a mechanical oscillation like a swing or the vibration of air in a bottle, which leads to a larger wave amplitude.
Exactly.
Can resonance be used for constructive or destructive means?
It definitely can.
Okay.
Think about musical instruments.
Okay.
They are designed to make use of resonance.
Right.
To amplify specific frequencies, creating the sounds that we enjoy.
Right.
However, resonance can also be destructive.
Oh.
A classic example is the Tacoma Narrows Bridge.
Right.
It collapsed because wind caused it to resonate at its natural frequency, leading to increasingly large oscillations.
Wow.
That eventually broke it apart.
Okay, so resonance can be incredibly powerful.
Right.
Now, how do periodic motion and all these concepts we've discussed relate to how fast a wave travels and things like the Doppler effect?
Okay, so the speed of a wave is mainly determined by the properties of the medium it's traveling through.
Yeah.
In a uniform medium, the wave speed is constant, as we noted earlier.
Right.
However, if the medium changes, like when light moves from air into water, the speed can change.
Yeah. Okay.
Even though the frequency of the wave stays the same.
Wait, the speed changes, but the number of cycles per second stays the same?
Yes.
So if the speed slows down, what happens to the wavelength?
Okay.
Since speed equals frequency times wavelength.
Precisely.
Okay.
If the frequency stays the same and the speed decreases, the wavelength must decrease to maintain that relationship.
Right. It's like the wave is getting compressed.
Okay, got it.
Yeah.
And I know that sound travels at different speeds depending on what it's traveling through.
Exactly.
Right.
As your notes pointed out, the speed of sound in air is about 343 meters per second.
Okay.
At standard temperature and pressure.
Right.
But it's not constant under all conditions.
Okay.
It increases with increases in pressure, temperature, and density of the medium.
Okay, so denser, hotter air transmits sound faster.
Right.
That makes sense.
Yeah.
Now, what about the Doppler effect?
I hear this all the time with sirens, but how does it relate to frequency and the motion of the source or the person hearing it?
So the Doppler effect is a shift in the perceived frequency of a wave whenever there's relative motion. Between the source of the wave and the detector or observer.
Like the siren moving towards me changes the pitch.
Exactly.
Okay.
As your notes explain, if the source and the detector are moving toward each other, the frequency heard by the detector is higher than the frequency emitted by the source. If they're moving away from each other. The frequency heard is lower. This is because the motion either compresses or stretches the wavelengths of the sound waves.
That's why a siren sounds higher in pitch as it approaches.
Yes.
And lower as it moves away.
Right.
The sound waves get compressed or stretched due to the relative motion.
And your notes even include the formula for the Doppler effect. F prime equals F times V plus or minus VD.
Okay.
Over V plus or minus VS.
Okay.
It might look intimidating at first glance.
Right.
But it's actually pretty straightforward.
Okay.
The F prime is the shifted frequency you hear.
Okay.
F is the original frequency emitted by the source.
Okay.
V is the speed of sound.
Yeah.
VD is the speed of the detector.
Uh-huh.
And VS is the speed of the source.
Okay, that makes sense.
Yeah.
What do the top and bottom signs mean?
So use the top signs.
Okay.
The plus on top and the minus on the bottom.
Mm-hmm.
When the source and detector are moving towards each other,
okay,
that will give you a higher perceived frequency.
Right.
Use the bottom signs.
Okay.
The minus on top and the plus on the bottom.
Yeah.
When they're moving away from each other,
right,
that will give you a lower perceived frequency.
Okay, that makes sense.
Yeah.
So even though the source is emitting a wave with a constant frequency,
right,
determined by its periodic oscillation, our perception of that frequency changes because of the motion.
Exactly.
The underlying periodic motion of the sound source remains constant.
Right.
But the observed wave frequency shifts because of relative movement.
Right.
Now, what's an application of the Doppler effect outside of sirens?
So radar speed guns use the Doppler effect
to
measure the speed of cars.
Right.
They send out a radar signal
and
measure the frequency shift of the reflected signal to determine how fast the car is moving.
Wow.
It's also used in medical imaging.
Oh, wow.
To measure blood flow.
That's incredible.
Yeah.
Okay, now I want to shift to talking about wave behavior.
Oh.
Specifically superposition and interference.
Okay.
Then standing waves.
Right.
What's superposition?
So the principle of superposition is fundamental to understanding how waves interact.
Okay.
It says that when two or more waves overlap, the resulting wave is simply the sum of the individual waves.
So they just pass through each other, but while they're in the same space, their effects combine.
Exactly.
Okay.
And this leads to interference.
Okay.
If the waves are in phase, meaning their crests line up with each other, and their troughs line up with each other, you get constructive interference.
Okay.
The amplitudes of the waves add together, creating a wave with a larger amplitude.
Right.
It's like two people pushing a swing at the same time.
Crests meeting crests.
Yeah.
Troughs meeting troughs.
Right.
They reinforce each other.
Exactly.
What happens if they're out of phase?
If the waves are out of phase, the crest of one wave aligns with the trough of another. You get destructive interference. The amplitudes subtract.
Right.
And if the amplitudes are equal, they can completely cancel each other out.
Two sound waves canceling each other out. That's wild.
Absolutely. That's why noise-canceling headphones work.
Oh.
They create a sound wave that is exactly out of phase. With the ambient noise.
Right.
Leading to destructive interference. And reducing the noise you hear.
That makes sense.
Right.
And then what about standing waves?
So standing waves are a special case of interference. They happen when a wave is reflected back on itself. If the conditions are right.
Yeah.
The incident wave and the reflected wave interfere in a way that creates a pattern of points that appear to be stationary.
Stationary points, I see in my notes that those are called nodes.
Yes. Those stationary points of zero displacement are called nodes. The points of maximum displacement are called antinodes. A great example is a guitar string.
So when I pluck a guitar string, it looks like it's vibrating in place.
Exactly.
With certain points along the string not moving at all.
The vibrations travel along the string. And are reflected at the fixed ends.
Right.
These reflected waves interfere with the original waves, creating a standing wave pattern with nodes at the ends and one or more antinodes in between. The frequencies at which standing waves can be sustained on the string are related to the length of the string and the speed of the wave on the string, which in turn is related to the tension and mass of the string.
So everything is connected back to the idea of periodic oscillations and wave propagation?
Exactly.
It's incredible how the fundamental idea of periodic motion is woven into the very fabric of waves.
Right.
From how they're created to their characteristics, speed, and even how they interact. The concept of things happening in a predictable, cyclical way is key.
What's fascinating here is how these phenomena, like the back and forth of a pendulum and the energy traveling as sound, are connected by these principles of repetitive motion, energy transfer through waves.
It's like the universe has these fundamental rhythms.
Exactly, whether we're talking about a mechanical oscillation or a propagating disturbance, these rhythms dictate what we see and hear.
Exactly.
So for you, the listener,
yeah,
I hope you can now see the unseen connections between seemingly separate areas of physics.
Exactly.
Maybe things that seemed like isolated ideas. A swinging pendulum.
Right.
A ripple in water.
Yeah.
The sound of music.
Yep.
Are underpinned by these basic principles of repetitive motion and wave-like energy transfer.
And this raises a question. How might these ideas of periodicity and wave behavior show up in areas beyond physics?
Yeah.
Think about the cycles in nature, like the seasons or the tides. Think about patterns in data, economic cycles, or even trends in society.
Wow.
What other hidden periodicities might be at play around you, shaping the world in ways you haven't thought about before? That's a great question. I like it.
Okay. Definitely.
All right. Well, on that note, thanks for joining me on the deep dive today.
It was a pleasure.
All right. Have a good one.
Okay, you too.
Bye.
Bye.